Ladies and gentlemen, welcome to the Geological Society of London and to this, the 8th 2016 Society London lecture entitled Water on Mars. It's also, as you might have noticed from the various adornments in our entrance hall, Earth Science Week, and this is one of many events that are happening across the country, so have a look on our website to find out what else is going on. My name's Sarah Day, and I'm the science communicator here at the Geological Society, and it's my pleasure to introduce tonight's speaker, Dr. Matt Baum of the Open University. Mars was once thought of as Earth-like, with forests and oceans, and then as a dying desert planet whose desperate inhabitants dug canals to carry water from the poles. I'm looking forward to hearing more about that later. More recently, Mars has generally been perceived as being arid and dead, yet lately news stories about liquid water on Mars regularly fill the science pages. This is because the question, was or is there life on Mars, hinges on the presence of water. Matt Baum is senior lecturer at the Open University. His first degree was in physics with space science at University College London. He moved to UCL's geology department to do a PhD based on laboratory and remote sensing studies of tectonism on Venus. He followed this with a postdoc at Arizona State University, where he began studying Mars. Since then, he's held research positions in the USA, France, and the UK prior to being appointed to the Open University in 2007. His main research interests relate to recent Mars, especially aeolian and ice-related processes, but recently he's been working on ancient Martian landscapes, mapping potential landing sites for the ExoMars 2018 rover. I'm hoping we'll hear more about that as well. Ladies and gentlemen, please welcome Dr. Matt Baum.
Okay, thanks very much for that introduction. Are we alone in the universe? Is Earth the only planet where life ever took hold? Now, these are big questions, and over the last 20 years, I've spent my time looking at planetary surfaces, trying to understand how they've evolved, and these questions keep recurring. So what I'm hoping to talk to you about today, and to show you, is that by studying water on Mars, we can go some way to answering some of these questions. So I'm going to begin by asking, well, do we care about water on Mars? And if so, why we should? I'm going to give a bit of background about Mars and Mars exploration. And then I'm going to talk through the geological history of Mars and the role of water on the surface. Finally, I'm going to talk a little bit about future exploration, and in particular, ExoMars. Right, let's get the buttons right. So first of all, I'm just going to show a video. The first part of this video is real footage. The second part is an animation. This is from the Mars Science Laboratory rover's journey to Mars. That launched in 2013. So if we could start that video, please. So here we go. It's launching. People are very excited. They care about water on Mars. It's a very dangerous part of the mission. It's an extremely expensive thing to do, to launch a rocket. And now the rocket's made it clear of Earth, and the upper stage is propelling the spacecraft containing the rover, there it is, on its way to Mars. Now, it takes 6 months to get to Mars, and now it has to land through the Martian atmosphere. It's a very difficult environment to traverse, but also, because it's got an atmosphere, that does provide certain benefits. It means you can use a parachute to slow you down on the way down. There goes the parachute. So all good technology, all very sensible. But now, something audacious happens. It just drops the rover, and the rover's now flying on its own. And now something even more wacky happens. The sky crane lowers the rover to the floor, essentially on wires. Little explosions blow the wires away, and then the sky crane goes off. Now the rover's on the ground and ready to go. Now, I don't suppose anyone remembers this, or perhaps somebody was here in London for one of the launch events that we did whilst this was happening. But I remember being on stage and my fingers crossed because none of us could believe that this audacious, outlandish system for landing was ever going to work. But of course it did work, so that's a good thing. And this rover is now on Mars. Now, it's also known as Curiosity, launched in 2012, still going strong, collecting science. It cost $2.5 billion and took hundreds of people a good chunk of their lives to build and test. It's the size of a small car. It's nuclear powered, And inside it, it's essentially got a very well-equipped analytical laboratory. So it's got a mass spec, gas chromatograph, X-ray diffraction instrument, so it can measure bulk and minor element composition and also look at the minerals. And why? Why did these people go through all this time, spend all this money, and basically come up with the most groundbreaking designs? Well, look what the science aims were: explore past habitability and examine the role of water on Mars. So NASA thinks it's important to look at water on Mars. Why? Well, I think this is the main reason. Astrobiology. Astrobiology is the study of life outside of Earth and also encompasses the origin of life on Earth. Now, it's really hard to study the origin of life on Earth because we don't have very many ancient rocks from the period when we think life was getting going. Mars, however, has a lot more ancient rocks, and it's kind of, it's broadly Earth-like, so it seems like a good place to go. So it's a planet we could go to look for past or present life to compare with Earth. Now, interest in Mars and life on Mars was stirred even further about 15 or 20 years ago when this was found. It's a meteorite. It's called Allen Hills 84001. And when it was brought back to the lab, little things like this were found. Now, they're much smaller than terrestrial microbes, but they seem to be intrinsic to this Martian meteorite. So, of course, there was a lot of news about this. Could there be life on Mars? Now, since then, other hypotheses have come through that could explain these structures without life, but it's still in debate. But I think the key thing to think about is it made us really realise that as a planet, we care quite a lot about life on Mars. Now, if we discovered life on Mars and we found it to be similar in its genetic composition to life on Earth, that would be exciting. But if we found it to be totally different, if the origin of life on Mars was very different to that of the Earth, the two had evolved independently, then that's a really big deal, because the chance of life evolving independently on two planets essentially next to each other and the origin of life still being rare is essentially zero. So if we find life on Mars and it's evolved independently, that basically means there's life throughout the galaxy. And whether you're a planetary scientist or whatever, I think most people consider that to be quite a big deal. Now, most astrobiologists think that we need liquid water as a prerequisite for life, not just to get going, but to reproduce, disperse. Life can survive without liquid water in glaciers, frozen solid, but really you need liquid water if you want to develop and thrive. So follow the water is something that astrobiologists tell us we should do. Now, there's another reason why I think we should care about water on Mars, and that's exploration. We are going to go to Mars as a species at some point, whether it's NASA or with one of these private enterprises that seems to be very good at producing nice graphics. But one of these private enterprises might work. They do things differently, and some of them are sort of based on a sort of a game show, and some of them are more based on a single very rich individual. But it's a different way of looking at things, and eventually we're going to go to Mars, one way or another, private or funded by the state. So we're going to need water. Astronauts need water, or at least ice, for lots of reasons. Food, drink, fuel, well, pretty much everything, really. You can't really survive without water. But also, what if we were to find liquid water on present-day Mars, and our astronauts went there? Our astronauts who are covered in microorganisms, they would contaminate possibly Martian water. And the last thing we want to do is, if we're trying to work out whether life on Mars has a same origin or a different origin, is to contaminate them areas with terrestrial microorganisms. So really, if we find liquid water on Mars, does that mean we have to stop exploring those areas and prevent astronauts from going to them? Because that might ruin our chance of ever knowing whether life got going on Mars independently. It's called planetary protection, and it's become a big thing recently. So, Mars. Just a bit of background, not too much. It's the fourth planet from the Sun. It's got a very thin atmosphere. It's made entirely of CO2, or nearly entirely of CO2. Gravity is much weaker than that of the Earth. It's very cold. Annual mean temperatures are 50 to 60 degrees C. And we know that it's got lots of big geology. It's famous for having the largest volcano in the solar system, the largest canyon system in the solar system. And perhaps because it's so near, and it's not quite as difficult to get to as Venus, it's the best explored planet after Earth in the solar system. Now, this is a beautiful picture. I think this is how lots of people see Mars, but it's not how I see Mars, and I think it's not how planetary scientists as a whole see Mars. I see Mars more like this, as a map, colour-coded by topography. So here, blues are low, reds are high, and up here, whites are the very highest. You might recognise Olympus Mons over here, Valles Marineris here. So these are quite famous landmarks on Mars. So what can we see from this? Well, for a start, we can see that the northern lowlands are very low. That's why they're called the northern lowlands. And the southern highlands, can anyone guess? They're very high. Also, the highlands have a lot more impact craters. These little circular things, these are the scars of enormous meteorites smashing into the surface millions or billions of years ago. And what that means is that this is probably an older surface, because the longer a surface is exposed to space, it collects more impacts. Now, this is modern Mars. What about ancient Mars? What about the beginning of exploration of Mars? Well, we knew Mars was something other than a star right back in the Egyptian times, but we couldn't really look at it as a geographical entity until the telescopic era. So this map here, a nice map from Schiaparelli, made about 100 years ago, and took him several years to complete. What we can see here are there's a lot of linear features. He called them canali. He thought they were some kind of channel. Now, canali doesn't mean canal, Italian. It just means channel, so a linear feature. Lots of different areas with different albedo, dark patches, bright patches, and you'll note that this is the northern plains here, and this is the south up here, because obviously if you're looking at it with a telescope, it flips it over. Like I said, Schiaparelli, he didn't say really too much about whether these channels ever had water in them. Somebody who did say that was Percival Lowell, and he was a firm believer in water on Mars, and he thought that these linear features were actually canals, and that they were draining water from the ice caps at the north towards areas of civilization, to irrigate crops, keep people's houses, the way they wanted them to be. So he believed that there was an intelligent Martian culture, but the planet was drying out, and so they were doing anything they could to keep surviving. And actually, you look at this is front page news. So he was obviously considered to be quite an expert on all this. And interestingly, this view actually held sway into the 20th century to some extent. And then came the space age. Now, the space age threw a few spanners into the workings of Pohl's hypothesis. And there were two NASA missions in particular that really shaped our modern view of what Mars looks like. The first was Mariner 4. And when Mariner 4 took the first spacecraft-based pictures of Mars, it came up with something like this. Now, it's quite a grainy image, but it's just enough to see sort of some impact craters, possibly the rim of a larger impact crater here. The general impression really was that it was moon-like, and this was sort of confirmed by the next two spacecraft that went to Mars. And it really put the nail in the coffin for, for canals on Mars. Excuse me. But the next one was Mariner 9. Now, Mariner 9 was a lot more interesting. It found volcanoes, faults, tectonic features, layered terrains that might be sediments. And it also found river-like channels, such as in this image. Now, what you've got to remember here is the sun is coming from this direction. So this is an impact crater with a rim. So this is a hole in the ground, and the light is catching the opposite side here and causing a shadow here. If you see it as a dome, instead of a hole in the ground, you have to stand on your head. Or just wiggle a bit. So what hopefully you should be able to see is that this is a channel. It's carved into the ground. And it has a sort of a sinuous profile, but the most interesting thing is there are smaller sub-channels coming into it, so little contributory networks. So basically, that looks very much like the sort of thing you would expect with a river valley system on Earth. So water on Mars was back in the game. So that's exciting. Since then, there have been a heck of a lot of missions to Mars. So what we show here, this is 1960. This is the future, 2020. Each of these lines represents a mission. Each one that ends in a cross is a failure. A tick is something more happy, a successful mission. The red ones are Soviet and the blue are United States. You can see that the closer they get to Mars, it tells you a bit about what the different mission was, so rovers, landers, orbiters, etc. The big thing to see is how many crosses there were in the early parts of Martian exploration. To me, it beggars belief they even bothered carrying on. I mean, if you've got a sort of 80% failure rate, you may think this is just too hard. But the tenacity of these people was quite astounding. They sent mission after mission. And I think that shows that they could see there was something really interesting about Mars. Now, recently, we've had a lot more success, and I hope we don't get too blasé about this, because there are more missions coming up in the next few years. So hopefully they'll also be ticks. Now, I look at pictures of Mars mainly. That's kind of what I do. I interpret the geology from images. So for me, I'm always excited when a new instrument comes online or a new mission comes and says we can improve on what you had before, or a new planet is explored with a whole bunch of new imaging data sets that I can get my teeth into. So back in 1971 with Mariner 9, the best resolution you could get was 100 meters per pixel. Now, you could barely see a football stadium with that kind of a data. It didn't have any global imaging. Now, a bit later on, the Viking missions had very good imaging, but the global was still relatively poor. The thing that I'm most interested about, the thing that for me changed the game, is in 2005, the Mars Reconnaissance Orbiter spacecraft. It had the HiRISE instrument, which had, this isn't a typo, 25 centimeter per pixel imaging resolution. So that's better than anything you'll get on Google Earth today. But it also had the context imager, which was meant to be a partner. And in some ways, that's even more important, because that has 6 meters per pixel resolution, but over the whole of the planet. And between those two things, that enables us to target on things that we really want to know about, and also have a wonderfully detailed synoptic view of the whole planet. Interestingly, on Mars, a lot of the older features are also the biggest features. So the features we've known about for longest. And the youngest features we're only starting to understand now, because it's only been in the last 10 years that we've had the resolution that's capable for us to actually see them and understand them. So in some ways, the exploration timeline parallels Mars's geological timeline, which is a handy link onto Mars's geological timeline. So Mars's geological history is divided into periods in the same way as Earth is. On Mars, these are based on the density of impact craters. If you remember, I spoke about the more impact craters an area has, the older it probably is. And it's really split into 3 main periods: the Noachian, the Hesperian, and the Amazonian. Now, on Earth, the different eras are based on various types of data, and also the presence of fossils. So obviously that's going to be a bit tricky for Mars. But we still managed to do it. And I think what's important to note is that this point here, when we think life was getting going on Earth, matches the Noachian period and perhaps the early Hesperian period on Mars. Now, there is a period called the pre-Noachian, but it's currently debated amongst planetary geologists whether there is actually any material available on the surface that we can see. So it seems like it's all fixed in stone, but it is still a work in progress to some extent. Now, this is a different map. This shows the rocks or the surfaces of different ages plotted on a Mars map. And as you'll see, in the north, it's generally the younger terrains. And in the south, it's generally Hesperian. So this means that the highlands, the Noachian highlands, are really old, and the northern lowlands are generally really young. So the question is, do these Noachian terrains show evidence for the action of liquid water? They were in place at about the same time that life was getting going on Earth. So these would be the places to go and look for, perhaps, if you wanted to find life. But it'd be nice if they actually showed some evidence of liquid water. There's the Noachian. And yes, surprisingly, they do show wonderful evidence for the action of liquid water. Let's start on the left here. So this is an impact crater, but leading into this impact crater are a variety of little valleys, and they're branching dendritic. They're made up of lower order branches feeding into higher order ones, and they all deposit in a basin. Now, I think this impact crater basin has been filled in more recently by something, but it shows the point that there's quite long incised channels that appear to be carved by a fluid. Similarly, in this image here, this is an even larger area, and what you can see here is many, many branches of channels, leading into one another, forming higher order channels, and then eventually most of them lead down here into one main trunk. You might be tempted to call that a river. And these are big, these things as well. They're hundreds of meters deep, they're kilometers wide, and many multiple branches. We think they form in the same way that these sort of things form on Earth, that you have to have water precipitated onto the surface. In the steepest areas, you form small low-order streams that then merge into larger streams and then on into small rivers and larger rivers. There's also an element of subsurface flow down slope, and eventually you get to a higher order trunk river which can carve through the landscape more. So does this mean there was rainfall on early Mars? Well, we're going to come back to that question, but if you looked at these channel networks, you would probably think there was. Now, where are they? Well, as you can see, this is another nice topographic map. Remember, blue is low, red and white are high. These little white lines, they represent these channel systems. This was a map done in 1995. I was trying to work out how many years ago it was, and I couldn't do that on the fly. But it was done from 1970s, 1980s data. So that means 240 meter per pixel data. More recently, this was updated using 100 meter per pixel data from Mars Odyssey, and 4 times as many channels were found. And you can see they're a lot more densely populated here now. But basically, the whole of the Noachian highlands have these channels all over them. Now, if we want to go even higher resolution, we can't do the whole planet. There's just too much data to look at. But we can look at different study areas. So this is some work that I've done with my PhD student, Joel, who I know is sat in here somewhere, to make sure I say it right. So when we went and looked at this is what we had before. And then we looked at these high-resolution images, and we found even more channels. And I think the more you look at in higher resolution, the more you find. You find small, low-order channels feeding into higher-order channels. It seems that the Noachian highlands are basically teeming with evidence for liquid water carving the surface. Now, if all these valleys were carved by liquid water, and they're all a few hundred meters wide and maybe tens of meters deep, hundreds or thousands of kilometers long, that's a huge amount of material that's been removed from the surface and taken somewhere. So for every cubic meter of material that has been removed, you're going to need 10, 100, 1,000, maybe tens of thousands of cubic meters of water to erode it away. So where did all that water go? Well, did it once fill a northern ocean? There's only one really big hole on Mars, and that is the northern ocean. So that would seem likely. So let's have a think. This is some work done by some researchers nearly 20 years ago. And what they did is they looked around the edge of the northern plains looking for morphological evidence for shorelines. What they were looking for were things like this. They're quite subtle. They look like little strand lines, little bathtub rings. You can just about make them out. So this area up here is it's the southern highlands. It's sort of a part of it sticking out. And this is the putative ocean. And so this is what they mapped out. This is just one example. They did this around the whole of the northern ocean region. And from that, they found there were 2 possible shorelines. There's a lower one here and an upper one here. By the way, Mars doesn't have a sea level, so 0 elevation on Mars is sort of an arbitrarily set level somewhere in the middle. So that's why we've got minus 2,500 as the elevation there. A lot of people weren't really convinced by this. It's fair to say they're quite subtle features you have to look for. But more recently, another bit of work has come on that kind of supports this. And this is looking at the concept of tsunamis. Now, imagine you have the northern plains of Mars and it's filled up with an ocean. and you have an enormous meteorite land in it, you're going to get a tsunami. You know, it's going to create an enormous wave. And so what these workers did was they looked for things that they thought were morphologies that might be associated with a wave coming up onto the surface and then retreating back again. So what we have here, so again, this is the highlands. Down here is the ocean. So the wave has come up here and it's reached this point here, and then it's drained back. So they argue that these channels are the drain back channels as the wave went back into the sea or into the ocean. That's not very convincing either, you might think, until you see what's up here. In this region here are enormous boulders. Now each of these bars is 10 meters, so that's the size of a house, that one. That's a pretty big house. So somehow something with a lot of energy has somehow pushed all these boulders up and left them in a band at this point, and then underneath that band there's all these drainage channels. So I think that that's a pretty plausible argument that there's been a tsunami. I can't think of any other process that could push all these boulders up and leave them stranded there with drain back channels beneath. So how do these look, these shorelines, when we put them on the map? Well, they actually fit pretty nicely to the valley networks. Most of the valley networks are above the edge of the sea, and that's quite a good thing. There's a few exceptions here. So that's a younger channel anyway, and these ones here are in a closed impact basin. So perhaps it wouldn't have had the same sea level as the Northern Ocean itself. So this is the dark one is the lower one, and the light blue is the upper one. So it does seem like all these bits of evidence are fit together to some extent to suggest there was a Northern Ocean. Now I think there's actually one bit of evidence that is much more of a clincher, and that is evidence from deltas. Now, as you can see over here, these are some terrestrial deltas taken in remote sensing data, Landsat I think, and they form essentially when a river meets a standing body of water, a lake, a sea or an ocean. Now Mars has deltas too, and you find things like this at the end of channels, which is just where you'd expect them. Some of them look quite like terrestrial deltas in some ways. So this one is a famous one, an Eberswalde crater. This one here has also got a nice sort of branching bird's foot sort of shape. This one up here is a bit like that as well. Others are a bit more simple. They're just like sort of simple fans. The channel is coming down here and depositing this fan. It's got a very strange flat top. Similarly with this one, and this one is sort of a multiple version of that. Now, what these workers did is they looked at the deltas, which, if you remember, normally fall in water around the edge of the Northern Ocean. Oh, by the way, this is another topographic map. This time we're looking down on the North Pole here. So this is the equator running around the rim here. This is the North Pole. And they found, quite surprisingly, I think, that all these deltas were at a very similar elevation, and at an elevation that actually matches the upper shoreline really quite closely. So it's very hard to think of a reason why all these different features that appear to be deposited in water should all be at the same elevation, unless there was one single standing body of water, which is an ocean. So personally, I think that's the best evidence yet for an ocean on Mars. I'm sure the debate will rage back and forth in the literature as it normally does, but I think that's a very good argument. Now, we don't just have to look at geomorphology to understand water on Mars. This is our old friend Alan Hill's 84001. It's a meteorite, as I said. It came from Mars. It was ejected from Mars by an even larger meteorite impacting into the Martian surface and sort of slingshotting it out into space. Eventually it landed back on Earth in Antarctica. It's a volcanic rock, so it was formed 4.1 billion years ago. And the good thing about having meteorites is we can take them to terrestrial labs where we've got all the kits we need. We don't have to rely on packing it on a rover. So some serious analysis has been done on this rock, and they found carbonate minerals, which are a little bit younger, 3.6 billion years old. So obviously a secondary mineral. And the conclusion here is that these minerals require the presence of liquid water to form. And so that liquid water must have been either in the subsurface or just below the surface, running through this basalt and depositing carbonates. So Actually, it may not be a basalt. I just assume all Mars volcanic rocks are basalts. It's a volcanic rock. We can do a similar study by looking at reflectance spectroscopy. Many of the instruments, many of the orbiters going around Mars now have instruments that can detect, to some extent, the types of minerals on the surface. This is a map of where they've detected certain types of minerals. All of these are alteration minerals that suggest the presence of liquid water. So we have phyllosilicates, chlorides, sulfates, and carbonates. Now, once again, you can see there's a very nice correlation here with the Noachian highlands. So that's, once again, we find that these minerals formed by liquid water are found in the oldest rocks in the Noachian highland. There are some exceptions, and they're normally, for example, here, where Valles Marineris has cut through the stratigraphy, revealing stuff on its walls, or in other areas where there's impact craters penetrating down through the younger material and finding older material beneath. I'm just going to talk one more thing about Mars Science Laboratory, basically because it's really, really cool. So this is a lovely image. It's a computer model, but this is not. This is actually a selfie taken by the rover by holding its arm out in front of it and snapping itself. It's taken a bunch of these. There's a whole number of them, but I think this is a particularly nice one. Now, it's full of analytical kits. It can do all sorts of clever stuff, but I think the biggest discovery was made as if it were just a geologist, just walking along, seeing an interesting rock, and went, I know what that is. So, near the beginning of its mission, it found a rock that looked like this. And around the rock were very smooth, rounded pebbles, and they were falling out of the rock. In the rock themselves, they were held in a matrix of finer material. And if you look at that and have a quick think, if you've done any kind of geology, you think that's got to be a fluvial conglomerate. These are stream-tumbled pebbles that have then been deposited at the end of a stream or within a stream. Other sediments have been laying on top of them. They've been pressurized. They've turned into some kind of a rock, then exposed by erosion to be revealed now. And that's a categorical signature of running water. Even if you saw that just out in the field, you'd feel pretty chuffed that you've seen something so diagnostic. So here's an Earth example, just for comparison. So I think, despite all its high-tech stuff, I think one of its nicest discoveries was just made with a good quality camera. So to summarize the Noachian, there's a huge variety of evidence, widely distributed, for liquid water being present in Mars's most ancient Noachian period, and actually slightly into the Hesperian a bit later on. So this is why Noachian regions are really being targeted by missions that are aiming to look for habitability or life on Mars. Now, I'd say there was probably even an ocean, but there's still some debate about this. I don't think we'll be able to solve this until we go there and drill into sediments myself. One thing that also is a hot topic is what the early Mars climate was actually like. I think everyone recognized there was a lot of water, but what was the early Mars climate like? One group believed the environment was a bit warmer and wetter than today. The point here being there was precipitation of rain or possibly snow, but annual melt, so that almost on a yearly basis, liquid water is being produced, forming long-lived rivers and lakes. Now, the counter-argument is that the environment was generally cold and icy with no liquid water, enormous ice sheets, but there are a few intense periods, maybe triggered by volcanoes or a giant impact event, that melted some of this ice, leading to shorter, wetter periods where all that geomorphic work was done essentially at once rather than over a long period. That is currently the state of the art, and we go to conferences and debate this stuff. So that's an ongoing question. So now let's talk about the Hesperian. So the Hesperian, here we are in the middle. It's kind of a teenage period. It's a period of change, much like my teenage years. So at the beginning of the Hesperian, it was very much like the Noachian, warmer, a bit wetter, probably. But by 3 billion years ago, it was a much colder, drier place. So why was that? Well, we think that was something to do with the lack of a magnetic field. If there was a strong magnetic field on Mars, it had ceased to operate by this time. And so the solar wind, which is illustrated by these dashes coming in here, was able to interact with Mars's atmosphere and essentially strip it away. That's what these green and red bits are. So, it lost a lot of its atmosphere. Any water that was evaporated from the surface and made its way up into the upper atmosphere was also stripped away, leading to basically a thin atmosphere and a cold planet. That doesn't mean there wasn't a lot of water during the Hesperian, though. There's a different style of activity. Now, these are what are called outflow channels. There's about 20 of them that are all were deposited or all carved out during the Hesperian. You can see here, this is a gouge into the bedrock here. There's another one running around here. You could probably even convince yourself that some of this around here was eroded away by a similar process. This is an image, so with the lighting from above. So these are craters. And this is a topographic map showing the same thing. Blue is low once again, and red is high. Now, what we can do, a thing I'd like to point out actually is how long this is. So this is a scale bar of 100 kilometers. So this thing, all the way down to its source down here, is 1,800 kilometers long, and it's hundreds of kilometers wide in places. Right? If you try and think of that on the scale of, the UK, for example, it's a pretty big feature. Now, what we can also do is, using the topographic data, we can do a profile. We can draw a profile across here, 2 channels and an island. So how deep are they? Well, this is 2.5 kilometers deep, and so is this. 40 kilometers across, about 20 kilometers across. These are huge canyons, bigger than the Grand Canyon in the USA. If you look a bit more closely, trying to understand some of the geomorphology, where these flows have met bedrock obstructions, they've gouged their way through them and left them in these wonderful streamlined forms. Now, when they're going over flat ground, they actually are just long, deep, simple channels. They don't have any contributory branches. They're not forming in a basin. In fact, they often start at a tectonic feature. They start at a chasm, a rift, a fracture zone, or sometimes an area that appears to have just collapsed to form a mess. And that's what we call chaos regions. So they don't seem to have anything to do with liquid being sourced from above. They seem to be to do with liquid sourced from below. In many cases, you can see teardrop-shaped islands. This is one of my favorite ones here. So this was once an impact crater, but this huge flood of water has gone past it. It's basically eroded it all away, only leaving a rim and a little trail of material behind it. Sometimes you even see enormous dry waterfalls. Now, what could cause something like this? Well, the only thing that can cause something like this is what we call a megaflood. Now, megafloods we've known about on Earth. The best example is the megaflood from Glacial Lake Missoula, which happened about 15,000 years ago in the US. It created the channel scablands. And here's just an example of one of the features that it formed. So the floods were coming down here and down here, and there's a sort of a channel system here. The floods were also going down this way. But basically, the power of the water was such that it eroded back right into these capping layers, forming these amazing horseshoe-shaped waterfalls. Each one of these, when this was active, must have been an impressive sort of Niagara-like waterfall. It would have been quite a sight. Now, the crazy thing is, those floods, they calculated them as being up to 10 cubic kilometers per hour. Now, I can't imagine what 10 cubic kilometers of water flowing per hour looks like. But on Mars, for the Cassi flood, it's 10 times more. And I can't even begin to imagine what 100 cubic kilometers of water looks like flowing per hour. The scary thing also about this image is it's only 2 kilometers wide, which when you compare it to the 100-kilometer wide things that we were seeing before, just gives an idea of the scale and the power of these flows of water. Well, really, that's it for the Hesperian, really. It did have some river-like groundwater activities, sort of similar to the stuff we saw in the Noachian, but really it was a period when the environment was changing and liquid water was playing less of a role. Nevertheless, these amazing megafloods occurred, and they were probably caused by something that enabled the water to be sourced from underground. So it could be geothermal, volcanic heating. If you imagine, there being huge permafrost zones underground on Mars, volcanic event could melt all that and release the water in vast quantities. Like I said, the scale of these is really hard to grasp. I mean, they've carved channels kilometres wide, thousands of metres or more deep, and they've plucked out rocks the size of houses and deposited them all over the environment. I think it's crazy. We're now going on to the Amazonian. So there's the Amazonian, the last period. It's cold, dry Mars. In the last 3 billion years, water was basically frozen. The atmosphere was too thin, and it was too cold for water ice to melt. It doesn't mean nothing happened, though. Even today, we know there's a huge amount of ice in the Martian soil. So this is a map created by a gamma-ray and neutron spectrometry instrument on board the Mars Odyssey spacecraft. And what it shows here is at the high latitude areas in the north and in the south, it's measured the amount of water in the top 100 centimetres of the soil. Now it shows here in these high latitude areas, it's about 40 or 50%. So you imagine that if you had a bucket and you dug up a load of soil, poured it out, about half of that would be ice. That's a huge amount of ice in the Martian soil. Lower latitudes near the equator, for example, there are some areas with more and some areas with less, but it's generally less than about 7% by weight. So today is part of the Amazonian, and so we know that today there was a lot of ice in the Martian soil, and that was actually confirmed very nicely recently by Phoenix lander. So this is the Phoenix lander. It's not a selfie, unfortunately. It's just a picture. But it had a little scoop, and it dug into the soil just a few centimetres down, and this is what it found. So here's the scoop, and you can see these little white patches it's dug up. Now, they could be light-toned minerals. They don't necessarily have to be ice. But when we look at this area here, which corresponds to that, a sol, by the way, is a Martian day. So Sol 20 and Sol 24, there's 4 Martian days in between. By this time, this little patch here has disappeared. So we think that it must be water ice, because the water ice under the Martian environment will sublimate away and disappear. So that's really good confirmation that the observations made by Odyssey are actually true. We've got field validation of a remote sensing measurement. We can also do this on a larger scale by using a different type of probe. So we can use meteorite impacts. Now we have access to this high-resolution, high-rise data set, 25 centimetres per pixel. We can target different areas and look for new impact craters, tiny ones. They're happening all the time on Mars. This one was about 8 metres across. That's about from me to that wall over there, perhaps. And when it was first spotted, everyone could see they had all this white stuff in the middle. But just then, a few months later, all that white stuff had gone. The argument here again is that it evaporated away or sublimated away. This is slightly lower latitude, so this is more like 50 degrees north, whereas Phoenix was at 68, I think. But it's really showing that there's a huge amount of ice in the whole of the northern plains and probably in the south as well. Now, when you've got that much ice in the regolith, it has an effect on the surface, though has a geomorphic effect that we can see. These are orbiting images again, or this is an orbiting image of Mars. And what you can see is these wonderful fracture patterns, almost like polygons. You can also see smaller pits appearing at the edges of the polygons, and then superposed on them, or perhaps these are superposed on those, these scalloped shallow pits. Now, we think these are formed because when ice cements the regolith, it gives it a certain amount of mechanical strength. And then over an annual cycle, it warms up and it cools down. It's warmer in the summer and it's cooler in the winter. And stresses can build up, which can fracture this icy soil. And by having many cycles of this, you can get these wonderful polygonal patterns building up. And the pits, they're probably to do with ice as well, because if the ice is ever exposed to the Martian atmosphere, it's going to sublimate away. You're going to lose volume, and so if you lose volume, stuff is then going to fall back into the voids that were left. So across the northern plains of Mars, you see very similar terrains to these, where you have fracture patterns, and pits of various different types. And what it's showing is that there's a sort of an ice cycle of ice being removed and redeposited and removed and being redeposited at a global scale. Now this is the dry valleys in Antarctica. Very similar situation. It's very dry, it's very low humidity, it's very cold. And this is a debris-covered glacier. And here, again, you can see these polygonal patterns. And terrestrial analogues are always a really important thing in planetary geology, because we like to know that the crazy ideas we're putting forward for Mars at least have an analogue on Earth. It's very reassuring. Now, looking a bit of a larger scale, there are lots of glaciers on Mars that are formed in the Amazonian, but they don't appear to be like most terrestrial glaciers. They don't appear to be wet-based. They appear to be cold and dry-based. So here's an example here. So what you've got is you've got an impact crater and another impact crater, and ice has built up in this one, and it's gently flowed down into this one like toffee. There's no evidence for any liquid water involved. It's purely the fact that over long periods of time, if you put ice on a slope, it will begin to very slowly deform, creep down according to gravity. Now, it may not be pure ice. It's probably a mix of ice and debris, or it may be ice covered by debris. Here's another example here, a smaller example. This is a small valley in the side of a larger valley. And again, ice is accumulated up here, and it's flowed slowly down onto this valley floor. So that's generally the way people think about Amazonian ice. But what about liquid water? Did the ice ever melt? Well, since about 2000, we've had access to higher resolution imaging. And it's changed the paradigm slightly, I would say. There seems that there are more observations now of things that could be to do with melting of ice. So this is what's called a gully. It's a bit of a catch-all term. This is sort of a classic gully morphology. So you have an alcove at the top. So this is the top of a crater rim up here going downhill this way. The alcove is where material has been sourced from. You have a chute or a channel. These are often sinuous, often have branches. And then you have a period of an area of lobate depositional fans. And sometimes these have features on them that look like levees that seem to suggest that it wasn't just liquid water, it was sort of a mudslide or a slurry that forms these depositional fans. Often you have multiple channels in the same area. Now, as you can see, they come in all different shapes and sizes. Some of them are very linear, like this, and these ones just form in sand dunes. Now, these may not be formed by liquid water at all. There's a lot of debate about that. But some, like this, are clearly cutting back into bedrock. You can see the rugged bedrock here, and the gullies forming down there and depositing on the bottom. So that's some pretty good evidence that liquid water was involved. And these things are only a few million years old. So normally less than 20 million years. That's kind of yesterday, geologically speaking. Certainly very, very late Amazonian. Other features that have been spotted include solifluction lobes. So this is a picture from Svalbard. Svalbard's also known as Spitsbergen. This is the top of a valley. And what you've got here is you've got these wonderful sort of loop-shaped forms sort of cascading down the valley. Now, these are actually made up of lots of little rocks, and they form by a combination of freezing and thawing of the upper part of the soil and gravity dragging things down. So it's a combination of slumping and freeze-thaw cycles creates these crazy loop shapes. This is aerial photo of a similar area in Svalbard. Here's the valley rim up here, so we're going down valley here. You can see these nice loops, but when you look at them in higher resolution here, you can actually see they're made up of little rocks. And I have actually been here, and I have actually been up to these things, and I can tell you they are definitely made of rocks. And then, surprise, surprise, here on Mars, we find a similar thing. So this is an impact crater again. Crater rim is here, down into the center of the crater. And you can see lots and lots of these loop forms on the side of the crater. And then, again, when you go down and look it up close, these are made of very small rocks. And it's very hard to imagine any other process that can create forms like this other than solifluction, which is based on freeze-thaw and gravitational slumping. Now, if you have freeze-thaw but not gravitational slumping, you can get sorted stone circles instead, or polygons. So this is a picture from Mars, on this little low plateau here. So just half a mile or so across, there's many, many circular shapes that appear, when we zoom in, to also be made from little rocks, little boulders. They're sort of set into a darker area around, and they form very well-defined circles. Now, aside from thinking that aliens came and moved them into circles to look after their sheep or something, there's got to be a natural explanation. And the natural explanation, again, comes from cold climate zones on Earth. Once again, we're in Svalbard, at least over here, and here you have these most amazing stone circles formed. Now, these really are the most impressive things I've ever seen. They are a metre or two wide. They're made of sort of broken up, sort of cobble-sized pieces, and sometimes they're perfectly circular. And they just look like somebody has put them together as an art project. But actually, they're naturally occurring, and they form purely by the action of freezing and thawing of ice-rich soils. Now, normally they're rarely above 5 metres, whereas the examples I showed from Mars are more like 20. Now, this is a person here for scale. So this is in Canadian high Arctic. I apologise for the quality of the picture. But this is a sorted stone circle that's much, much larger, definitely of the order of the ones that we saw on Mars. So I provide some good analogue for Mars and suggest that it isn't too crazy to think you could get sorted stone circles that big. Now, I said glaciers on Mars were always cold and dry. Well, this is from some work I did with an Irish colleague of a glacier that we think wasn't cold and dry. So here you have a sort of a valley going along here. Here's the remnants of a glacier, this texture here, and we think that it actually extended further out to about here. You can find similar textures like this left hanging around here. And also there's a sort of a trench that it's carved. Now, at the moment it looks like a pretty normal pile of Mars icy stuff. But the thing that's important is actually down here. When we zoom into here, this is over here, what we see are these sinuous ridges. They twine into each other. At some points they form little beads, so little short sections, and they're of the order of a few kilometres long. Now these are very, very reminiscent to landforms we see on Earth called Eschars. So here's some example of Eschars. Eschars form underneath glaciers, and they are the sediment that's left when a subglacial river has run dry and the glaciers moved away. So there was a glacier up here, and in front of the glacier are these eschar forms, very similar in scale. This is a very ancient glacier, eschar. So this is in Ireland, and funnily enough, trees like growing on eschars. So these tree shapes have actually picked out the ridges beneath them to show the pattern of the eschars. I think this is the most convincing one. This is in North America, and what they've done here is used airborne LiDAR, so they've used laser remote sensing to measure the height of the surface, but to penetrate through the trees to get the bare surface. And these look remarkably similar to the eschars that we see here. Now, just to give you a better idea of what an eschar actually is, I found this picture on the internet, but what this is you're inside a glacier, in essentially a long cave inside a glacier, and it's quite cold now, because if it wasn't cold, this cave would be full or partly full with water. So you can imagine going back up into the glacier, following this cave system, and it would trace out an underground or an underglacier river. So imagine that. You can see there's quite some big blocks and things in here. And then imagine the glacier being removed. And then looking down, what you'd see is you'd see the trace of where that underground river, underglacier river was, picked out almost like a pattern of blood vessels. And that, I think, is what we're seeing here. Now, there's also water on Mars today, liquid water on Mars today. What we're showing here is, again, making use of this high-rise camera. Now, what they've done here is they've taken pictures every few months, and then they've animated the difference. So this is the top of an impact crater rim, again going down into the crater this way. What I hope you can see are there these little dark features here that are very slowly extending and then fading. And this happens year to year, And the key thing to remember here is that they're not happening in one go. They're advancing over the period of several months. And that suggests that it's not a catastrophic flow like a landslide or a granular flow of sand just depositing down in an avalanche. It seems like something is trickling, it's propagating slowly. And that suggests perhaps water. Another thing that suggests the action of water is that they're active at the warmest part of the year on the steepest slopes. Also, we've managed to get some remote reflectance spectroscopy instruments to target these things. And they found a certain hint of a salty composition. And we all know that salts on Earth, if it's getting cold, you put salt down on the drive and you can get a lower freezing point. So it prevents freezing. And the same happens on Mars. And there are some minerals on Mars that can act as sort of super salts and can reduce the freezing point by 10, 20, or even 30 degrees C. So, this is the current understanding of these things. They're called recurring slope lineae. And what they might point at is a hint that there is liquid water on Mars today. So, to summarize the Amazonian, well, there's a few outflow channels, not very many, but really there's little large-scale action of liquid water on Mars. There is a lot of movement and deposition of ice. It's sublimating from the surface. It's being redeposited back on the surface in different places. But also, in the last sort of 10 or 15 years, we've realized that there's lots of evidence for the localized activity of liquid water on Mars, probably only in the last few million years. So this is very young and very small scale. Now, what does this mean for Mars? Well, and for life on Mars? Well, I talked about planetary protection. Do we need to stop going to these places where we might find things like recurring slope lineae? We don't want to fill them full of contamination. But of course, the other thing is that if life on Mars has evolved to cope with these this sort of environment, and the fact that water is only available every so often for a short period of time, if we want to find life on Mars, maybe we want to go into these places because that's where we'll do the science. So that's a problem for globally that we need to sort out. Just going to summarize water on Mars for you and its history. So in the Noachian, there's a huge amount of water, lots of valley networks, surface water. I didn't show any lakes, but there were lakes as well, and an active hydrological cycle. By the time you get into the Hesperian, it's colder, it's drier, but then, surprise, we have sudden mega flooding and formation of outflow channels, which is pretty exciting. In the Amazonian, it was cold and dry, nothing happened, but yet, everywhere we look with these higher resolution images, we can find hints that there might have been liquid water. So now I'm going to talk about the future, just briefly. ExoMars is a European Space Agency mission. It consists of 3 parts, a lander, an orbiter, and a rover. This is the rover. The orbiter will be going into orbit around Mars in about 1 week's time. Its aim is to look for trace gases, including methane, which is potentially an indicator of life on the surface if it finds methane. The lander is really there to demonstrate the technologies that are going to be needed to put the rover on the surface 4 years later. And that, I think, is going to be landing 5:30-ish in exactly a week from now. So that is exciting. Now, the rover is the thing that I've spent some time working on, really to do with the landing sites. Now, the cool thing about this rover is it has this drill, and it can drill 2 meters down below the surface to look for biosignatures. It can pick up a sample, ingest it into its analytical lab that it carries inside it, and look for signs of life. It's the first rover that is actually designed to look for biomarkers or life as opposed to just habitability in general. Excuse me. Now, because of that mission, having the right landing site is really important. So, we think the site has to be very ancient, so it's got to be Noachian, because we think that's the best time in Mars's history for life was getting going, and also when it was wettest. The site individually must show signs of prolonged water activity, and it's obviously got to be safe to land. We don't want to be another one of those crosses on that figure that I showed at the beginning of the talk. There are 3 sites in contention at the moment. They were picked from a sort of a game show style, eliminate one person every round. But the final decision and the final site should be made next year. Now, I lead one of these sites that's still in contention. I was the lead proposer, and this is Aram Dorsum. And I think this is a really cool site. So what you've got here, this is about 30 kilometres across. It shows a stretch of a branching and reforming channel. Looks very much like a fluvial channel, set into some finer grained material around it. Now, I say it's a channel, but some of the keen-eyed amongst you will have seen that it doesn't look like a channel. It's actually a flat ridge. Well, that's because it's what we call an inverted channel. So what's happened here is it's been something like a river, but as the river has dried out and become inactive, there's something about the channel bed that has meant that it's more resistant to erosion than the areas around it. So when you have millions of years of erosion, the floodplains around it are lowered, but the channel itself is lowered less quickly. So over intensive erosion, you end up with an inverted channel picked out against, in positive relief against the local area. Actually, this is, I think this is from Utah, and this is an example from Earth. And in fact, you see quite a lot of these things in certain environments on Earth, inverted channels that were once at the bottom, they were the bottom of a river, and now they're standing up as a ridge. So the really cool thing, I think, about Aram Dorsum, though, is not only does it have this really clear geological evidence for there being a river, but also it's surrounded by floodplains-like materials, and that's going to have fine grains, silts, and those would be really good for preserving biomarkers. And then, all this stuff around here, actually, this once buried this, and it's been stripped back away from it. So it's actually been protected from the Martian environment for much of Mars's history. So I think this is a good place to go. Now, we won't know whether it's a good place to go for 5 years, but or in fact, if they'll even choose it. But if they do choose it, then maybe in 5 years' time, I'll be standing here again telling you all about Aram Dorsum and the exciting discoveries ExoMars has made. So, thanks.
Thanks so much for a really fascinating talk. We are slightly out of time, but if there are any quick questions, if anyone would like to ask one now, there's one just here. Oh, sorry, I should say, please wait for the microphone before asking your question. That's just for the tape.
Yes, thank you for a fascinating talk. Mars is slightly smaller than the Earth, and yet the geological features on Mars are much greater scale than on Earth. Is that all down to erosion? But then erosion on the Earth is caused by atmosphere, and Mars's atmosphere disappeared a long time ago. Or is there another reason?
I think the reason things are so large is because Mars doesn't have plate tectonics. So, for example, volcanoes can build and build and build and build without being moved away and then recycled, and put back into the interior. Erosion on Mars is very slow compared to erosion on Earth. So things that are resistant to erosion can remain in place for a very, very long time. So we can see features that we wouldn't see on Earth. So I think it's to do with the sort of recycling at the crustal scale and also recycling at the local scale caused by the wetness and general erosiveness of the Earth's environment. So does that answer your question? Maybe.
Going to ask whatever happened to Canali. Are they a poor representation of anything that you've been saying, or were they purely imaginings from a very poor resolution compared with what you're getting today?
Well, I think it's partly imagining, and there are linear features, but I think it is mainly imagining. Now, interestingly, there are things called canali on Venus, and canali are up to 7,000 kilometres long, and they are a kilometre or so wide, and a few tens or hundreds of meters deep, and no one knows how they form. So that's the next canali puzzle. So.
Any more? And just one here at the front.
What are the arguments against that? The fact that they might be rivers? Could they be anything else?
That was my question.
Well, some people have put forward models of erosion for the valley systems by liquid lava. So it's remarkably difficult to understand how you can get a lava that is both runny enough to erode, it has to be turbulent, and yet somehow remains liquid for long enough to travel these very long distances. Now, it may be possible on Venus, and this is what the canali are presumed to be, because it's much, much hotter. The other thing it could be is glacial. So these channels could be carved by slower bodies of ice with water underneath them, but they don't show any of the morphology that you would find with glacial valleys. So I think the thing that people really don't understand, I think, is that you can't do planetary geology in the same way you do physics. You can't run an experiment and then find what you've got. You get what you're given, and you have to make your best hypothesis from that. And then you can bring in different other aspects that tie in, and as long as they keep tying in and the hypothesis keeps working, that's how we understand it. But of course, it doesn't take much to come in with a counter-argument that knocks it out the way, and then hopefully everyone then says, oh, you're right, we believe you. But currently, no one has knocked the river-style erosion hypothesis out the way yet. So that's the state of the art. But it's a really good question.
Thanks. We should probably call it a day there.
Okay.
But if there are any more questions, we're going to go next door for a glass of wine, and I'm sure Matt would be happy to answer them there. Thanks very much for coming, and please join me in thanking Matt Balm for a brilliant talk.
Harder the second time. Yeah?